Hello, everybody. Let's continue our discussion about the solar system. So far, we've learned quite a bit. We've learned about the objects that are in the solar system. We took a look at the 8 different planets and saw that there are 3 different types of planets: the terrestrial planets, the gas giant planets, and the ice giant planets. We learned about this thing called the Kuiper Belt and this thing called the Oort cloud. We also took a closer look at the small bodies of the solar system and learned some of the details about comets and asteroids. So we've had a pretty good general overview of what's in the solar system. Now let's step back and take a look at what the solar system looks like, what I refer to as the structure of the solar system. That's the theme of this video. And what we're going to be doing is we're slowly gathering all the evidence that we need to start putting together a coherent and logical theory for the formation of our solar system. So when I say structure of the solar system, what am I really meaning? And I'm asking, what does the solar system look like if we could sort of fly out of the solar system and take a look at it as a whole? And by that, I'm really talking about like what kind of shape does it have? And then what kind of patterns might exist within the solar system? Let's start with the shape of the solar system. The solar system is flat and disc shaped. All the planets are in relative isolation, and they're all on roughly the same orbital plane. I'll be showing you a picture of this here in a second. Or actually, let's just pop back. They're all on the same orbital plane. They're all in relative isolation. Think back to our very first video for this class when we scaled the solar system on a football field. We're talking about grains of salt and things like poppy seeds on a football field, and they all orbit on the same plane. So where it's flat, and since orbits are roughly circular, it's disc shaped. And this is true also for the Kuiper Belt objects. So, and if we were to take a closer look, and would notice that they all seem to orbit in the same direction. And I'll be repeating this as we go along. I just want to give you a sense of what I'm talking about whenever I say shape. And we also want to ask the question, what patterns might exist? And with this, we're really talking about one major pattern that we see in the solar system, that we have a gradient in chemical composition. That what the solid stuff of the solar system is made out of, and just what the planets in general, or what the objects of the solar system are made out of in general, has a nice gradient. It changes from one set of composition to another set of composition. And we have our terrestrial planets, then our gas giant planets, the ice giant planets, and the Kuiper Belt objects. So we have this nice gradient of composition throughout the solar system. And whenever we're talking about the gas giant planets, one of the things that we really want to ask are, what are the solid bits, the things that were first put together that went into planet building, or building the solid bodies of our solar system? So one of the things we really want to focus on are, what are the solid building blocks? And when we look at the gas giants, they have cores that are made out of solid material, except we can't see those because they're buried underneath enormous atmospheres of hydrogen and helium gas. So if we want to know what kind of solid building blocks there are available where the gas giant planets are being formed, we maybe don't want to look directly at the gas giant planets themselves, but we want to look at the moons of the gas giant planets that formed in the same region as the gas giant planets. So if we look at the moons of the gas giant planets, we see that they're mostly water ice and rock with some other things mixed in, like low temperature ices and organics. And the big thing, so why do we care about this? Why are we going to uh, look at the structure of the solar system? What is the so what, as one of my favorite teachers of all time would say? What is the point of caring about this? Well, what we're really working on is we want to build a theory of how our solar system formed. And to do that, we've been gathering up all the evidence of what our solar system actually is. What is its current state? What objects are in there? What are they made out of? So that's going to be our gradient and chemical composition. And what is the shape of the solar system? Because all of these are pieces of evidence for building a formation theory for the solar system. Because when we come up with an idea of how our solar system formed, when we have a theory of solar system formation, that theory better be able to reproduce what we currently observe in the solar system. If it makes us, if our the theory makes a solar system that doesn't look anything like ours, that's a pretty bad formation scenario, right? So really, what we've been doing here, and by taking this larger scale view of looking at the structure, is we are gathering the evidence so we can build a formation theory for our solar system, which is the entire subject of Unit to part 2. Okay, so let's go ahead and take a look. And I know I've already talked about this, but it's good to have a picture. So try to burn this into your mind. I've said the word orbital plane several times throughout the semester. And what that means is that everything orbits at roughly the same plane. So you can imagine we could put all the orbits. So here we have Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. And they all lie on the same plane. So they're all moving around the sun on roughly the same plane. And we call that the orbital plane, the plane in which the planets orbit. And it's flat. They all orbit on the same plane. There is a little bit of inclination, I'll show you that here in a second, where they might go above or below this plane because, it's a three-dimensional solar system, it's three-dimensional space. But for the most part, they all lie in the same plane. So we say our solar system is flat. And since all the orbits are roughly circular in shape, we say that it's disc-shaped. You can almost picture it like a flat plate. And this is something, so why? We have to ask ourselves, what would create that? What physical mechanism would flatten out our solar system? Why aren't we a spherical solar system? Why are we a flat disc-shaped solar system? What physical mechanism could flatten us out into being a disc shape? And then we can go into detail. So in this image over here, we're no longer looking at the solar system sort of edge on. It's like we're flying up out of the solar system and we're looking down on the north pole of the sun, or really the north pole of the Earth. So we're looking down on the northern part of the Earth. We're looking from the north down onto the solar system. And here we can actually see the shapes of the orbits, the distribution of the orbits. And we can start looking at things of like, oh, well, what ways are things rotating? What ways do the planets rotate? And what ways do they orbit? What is their revolutionary motion? And we see very, very quickly that we have what I call a organized spin sense. This isn't something that is out of a textbook. It's just a phrase that I came up with to describe what's going on. And what that means is that the rotation and revolution of the planets and asteroids and Kuiper Belt objects are all oriented in the same direction, especially with the revolution. Asteroids can rotate backwards, but that's a different effect that causes that. But if we look at all of the orbits of the planets, we're looking down the north pole of the Earth, which we've said several times. We look down on the north pole of the Earth, the orbit would be in the counterclockwise direction. The same would be true for Mercury, orbits in the counterclockwise direction. Venus orbits in counterclockwise. Earth, Mars, counterclockwise. And same for Jupiter, Saturn, Uranus, Neptune, all the Kuiper Belt objects and all the asteroids in the asteroid belt. They all orbit counterclockwise. What's going to make it so they all are moving around in the same direction? Some physical mechanism when our solar system formed must have set that motion in place. And if you look at how the planets are rotating, or if you look down the north pole of the Earth, it's rotating counterclockwise. Mercury, rotating counterclockwise. Mars, rotating counterclockwise. Jupiter, rotating counterclockwise. Saturn, rotating counterclockwise. So the planets are all rotating, or most of the planets are rotating counterclockwise. You might notice that I left out Venus in that list. It rotates clockwise, but why it rotates clockwise is currently a mystery of the solar system, but we have a pretty solid idea of what happened, that during the violent formation of our solar system, Venus got whacked by a very large object which flipped it upside down, which would also explain its very slow rotation. But so everything is orbiting in the same direction, and nearly everything is rotating in the same direction. And guess what? If we look at what direction the sun is rotating, counterclockwise if we're looking down the North Pole. So everything is orbiting in the same direction. Most everything's rotating in the same direction, and that's the same direction that the sun rotates. Almost as if everything was rotating in the same direction at the beginning. Again, we'll ask what physical mechanism can create this, and that's going to be key to building our theory of the solar system's formation. We also have non-circular orbits, but they are very, very, very close to circular with a few exceptions. The asteroids can have significant eccentricities. The Kuiper Belt objects can have pretty significant eccentricities. And Mercury has a large eccentricity, but other than that, they're all nearly perfectly circular, almost as if something is forcing orbits to be circular in shape or close to circular in shape. We also have that the planets are in isolation, almost as if something happened, or rather, they gathered up all the available material to form themselves and then left themselves as these little tiny island worlds of awash in the sea of space. And I want to hammer in a concept that's going to become increasingly important as we talk about our solar system. And this is the idea of orbital inclination. So let's imagine that we're looking at the solar system edge on. So we're looking down along the plane of the solar system. So we're looking down this edge. And what this image right here is just showing you the distributions of how tipped with respect to the orbital plane the planets are. The orbital inclination, how many degrees is tipped? And we've talked about orbital inclination when we talked about the moon's orbit has an orbital inclination of 5 degrees. The planets all have very low orbital inclinations, and you can see that is the distribution right here, that we are really flat. There's not any significant orbital inclination for any of the planets. And I want to go ahead and show you what the orbital inclination really means. So what I have here is a orbit as a green circle, and we're sort of looking at this at an angle. So this would be a circular orbit, but we're looking at the whole system as an angle. And then this yellow plane is showing the plane of the solar system, the orbital plane of the solar system. So if the orbit is perfectly in alignment, lies on the plane, the orbital plane, then we'd say the inclination is 0. Oops, wrong button. But that could be tipped, and here I'm tipping it this way. So at this point, the inclination would be 45 degrees. It's tipped with at a 45-degree angle with respect to the plane of the solar system, the orbital plane of the solar system. And the maximum you could tip one is 90 degrees. Sure, you could keep tipping it, but then we'd just say that it's like 80 degrees and 70 degrees, 60 degrees. And then you just be orbiting and look like you're moving in the opposite direction. So if you work counterclockwise, to look like it's clockwise. Not something I need you to remember for this class. I just want you to get a sense of what inclination is. So it's how tipped is the orbit with respect to the orbital plane of the solar system. Okay, so that's the general shape of our solar system. Now let's talk about this compositional gradient. The fact that we have our terrestrial planets, and then we have an asteroid belt that is mostly terrestrial, little tiny terrestrial worlds. Then we have the gas giant planets with their rocky, icy moons. And then we have the ice giant planets, whose primary composition are ices, and they also have rocky, icy moons. And then we have the Kuiper belt objects, which are rocky, icy objects, small rocky, icy objects that orbit past the orbit of Neptune. Let's actually take a look at what these things are made out of. What is their chemical composition? The terrestrial planets are rock and metal, and that metal is mostly iron. Almost no organics. Earth is one of the exceptions. But where they formed, they should have formed with no organics. Then we go to the gas giant planets. And the gas giants are mostly made out of gas, hydrogen and helium gas. However, if we want to know what solid bits would be in Jupiter and Saturn, and yes, they do have terrestrial-like cores, then we'd want to look at the moons of Jupiter and Saturn, and we'd notice that they're rocky and icy, mostly water ice. But you can get some things like carbon dioxide ice and things like that, especially once you get out to Saturn where it's colder. But we also start seeing the moons have organic molecules on them as well. So there are organics. And then by the time we get to the ice giant planets, not only do we have water ice, but we also have all these low temperature ices, methane ice, ammonia ice, CO2 ice, carbon monoxide ice, a whole slew of different kind of ices that exist only at really low temperatures. And then we look at the moons of the ice giant planets and we see that yes, they are rocky, icy as well, but they have more low temperature ices. And yes, there are organic molecules there as well. I mean, methane ice is an organic molecule. And then as we move even further out into the solar system, We have our Kuiper Belt objects, which yes, they have a rocky metallic bit to them, but they also are largely made out of ices. And we're not only talking about water ice here, which is a huge component of it, but other ices as well. The same sorts of things we saw in the gas giant or the ice giant planet moons. All of these exotic ices, nitrogen ice, methane ice, ammonia ice. So we see this gradient from just metal and rock to adding more and more ingredients as we go out. And I really want to hammer this in. So let's look at this one step at a time. We have our terrestrial planets, which are almost entirely made out of metal, mostly iron, and silicate rocks. Pretty simple. And then we move through our asteroid belt. The inner asteroid belt is very similar to the terrestrial planets. By the time we get to the outer asteroid belt, though, we have metal, silicate rocks. Now we have some hydrated silicates. We have some ice, although we are still looking for ice. We've only found it on a few asteroids. And we see organics in the C-type asteroids, the carbonaceous asteroids. The moons of the gas giant planets, they're made out of metal, silicate rocks, lots of water ice, some low temperature ices, and some organics. And notice that the ingredient list is just growing. With each time, the ingredient list is getting larger. By the time we get to the ice giant planets and their moons, we have metal, silicate rocks, water ice, a lot more low temperature ices. So we're adding to the list of low temperature ices, and we still have some organics. And then by the time we get to the Kuiper Belt, we have metal, we've got silicate rocks, we've got water ice, we've got even more low temperature ices, and we've got even more organics. So we have this nice gradient of adding ingredients, building blocks that these planets are in solar system objects are built out of. Our formation idea better be able to explain why we observe this compositional gradient. There must be some natural reason, some physics behind all of this, and really it's more chemistry in this case, physics and chemistry that defines this chemical composition gradient that we observe in our solar system. All right, so that is going to close out our view of our solar system for the most part, but we still have some work to do. Our solar system is only one data point on the number of planetary systems that exist out there. Our solar system is a planetary system. If we really want to get a good view of how planetary systems are in general, we need more than one data point. So moving forward, we're going to leave our solar system and take a look at extrasolar planetary systems. That's in the next video, and I will see you there.